Well, good afternoon. This is Wednesday, the 30th of August, 2017, 12:18 in the afternoon. We should have been in class 3 minutes now, but no one's shown up yet but me, so I'm going to go on and get started. This is supposed to be Cal 3, and we are hopefully finishing the preliminary stuff, the stuff that we didn't get to cover in Cal 2, but bring you up to speed so we can move along in Cal 3. Hopefully we'll finish this today, or get pretty close to it anyway, and get into real Cal 3 material. And we're starting today in section 12.3 in your text. This is page 645, and we're talking about the dot product and the angle between two vectors. And here is the slide that introduces, or at least a slide that introduces the dot product to you and gives at least one of its definitions. Okay? There's several ways to define the dot product. Here's one. Okay, you have two vectors, V and W. Any two vectors, V and W. The dot product between those two vectors, and this, the reason they call it a dot product, they use the decimal, the period, the dot in between the two. Remember, in multiplication, we usually use a cross, which is a time sign, or a dot for a time sign, or sometimes just write two letters next to each other, or a number next to a letter, or parentheses next to each other, or something like that. That represents multiplication. Several ways to do it. For vectors, we use two different ones. Well, we actually already have defined the scalar multiplication. That way we just write the scalar next to the vector. Okay? Now the dot product between two vectors, okay, you can't just multiply two vectors any old way. There's two ways. Dot product, which is vector V being A1, B1, C1, vector W being A2, B2, C2. Now these vectors could be two-dimensional, 15-dimensional. We're usually going to stick with 2 or 3. So if that's the case, the dot product is defined. It is a scalar. Dot product always turns out being a scalar. And it is A1 times A2 plus B1 times B2 plus C1 times C2. In other words, the product of the corresponding components of those two vectors, you add those products together and you get, that's what gives you the dot product. A scalar quantity. Now, in the old days, I remember hearing this be called the scalar product. That's not to be confused with multiplying a scalar times a vector. This is a vector times a vector giving you a scalar answer. And it's simply the sum of the product of the corresponding components. Okay? Now, here's some properties of the dot product. Okay? First, the zero vector, of course it would have to be the same dimension as the vector V. The zero vector dotted with V is the same as the V dotted with the zero vector, and that is the number 0, not the vector 0, because the dot product always produces a scalar. That's a scalar 0. And that's because, say, vector V is V1, V2, V3 are the components, but the zero vector would be 0, 0, 0, okay? And when you multiply 0 times V1 plus 0 times V2 plus 0 times V3, or V1 times 0 plus V2 times 0, so they all add to 0. Scalar 0. Okay, commutativity, I guess is how you say that, of two vectors, okay? Of the dot product of two vectors. If you multiply V times W, that's the same as multiplying W times V. So let's just say vector V is V1, V2, V3. Vector W is W1, W2, W3. Those are the components. When you dot product them together, it's V1 times W1 plus V2 times W2 plus V3 times W3. And if you do it the other way, W dot V is W1 dot times V1 plus W2 dot times V2 plus W3 times V3. And guess what? Because the V's and the W's are commutative, it doesn't matter. They're just, those components are just numbers. then it doesn't matter the order. You're adding those products together, you get the same result. Okay. Pulling out scalars. That could be called oh my goodness, I'm going blank. Distributing in reverse, okay? If you have lambda, the scalar lambda times the vector v dotted with vector w, that's the same as vector v dotted with the scalar lambda times w, and that's the same as scalar lambda times the dot product of v and w, okay? Now remember, with these dot products, it's going to be a scalar answer, and the first one would be a lambda times v1 times w1 plus lambda v2 times w2 plus lambda v3 times w3. Yeah, same thing. For the next one, it's v1 times lambda w1 plus v2 lambda w2 plus v3 lambda w3. So in other words, you can factor out the lambda, which gives you lambda times v1 w1 plus v2 w2 plus v, which is lambda times v dot w. Always scalars. The distributive law. Now here you have to be just a little careful, but not too bad. U dotted with the sum of two vectors, v plus w, would be the same as u dot v plus u dot w. Okay? Nothing real special there. And you can dot it on the other side, v plus w dotted with u. By the way, that would be component by component, v1 plus w1 times u1, both of those, plus v2 plus w2, that multiplied by u2, plus v3 plus w3, that multiplied by u3. And if you broke that down and redistributed, you'd find that's the same as v dot u plus w dot u. Okay, and again, the order really doesn't matter that much. Now, relation with length. Okay, this is something new and something quite usable. The dot product of a vector with itself, in other words, v1, v2, no, I'm sorry, v1, v1, which is v1 squared, plus v2 squared, plus 3 squared, that's the square of the magnitude of v, because the magnitude of v is the square root of v1 squared plus v2 squared plus 3 squared. So when you square that, you get the dot product of a vector with itself. A pretty useful property to hang on to and remember in the future. You'll be using that. All right. This is the figure that goes with example 1, I think. Okay? No, it isn't. It's after example 1. Example 1 is just doing some calculations. The dot product v dot w is related to the angle theta between v and w. Okay? That angle is not a uniquely defined angle because, remember, you can add or subtract 2 pi to any angle and get a coterminal angle which has the same values of the trig functions. So here's what that relationship is. I'm sorry, I probably should have blown this up. All right, by convention, the angle between any two vectors is chosen such that when we refer to it, they've got this wrong. Okay, sorry about this. Duh. They have it right in your text, but wrong on the slide here. The angle theta between two vectors is chosen such that theta is always between 0 and pi. So you choose, this should be a theta there, and I'll go on and reduce it and then correct that. Let me get my pen back in dark color. This should be theta, not pi. Okay, obviously that's not pi. So by convention, the angle theta between two vectors is always chosen to be the one that is either acute or obtuse. Nothing beyond 180 or pi. Okay. All right. That's what we just said. The angle between two vectors is always chosen to satisfy theta is less than or equal to, 0 is less than or equal to theta is less than or equal to pi. Okay? Which makes it pretty interesting. I was thinking that let's see. I don't think it's that's enough said about it. I was going to add something else, but I don't think anything worthwhile to say there. Angle between any two vectors is chosen to satisfy. So if you have two vectors, yeah, I know what I was going to say. It's either going to be an acute or an obtuse vectors. Nothing, a vector in quadrants 3 or 4, you will use the that doesn't have a name for one, that if it's in quadrant 3 or 4, you use basically what we normally think of the negative angle down there, but you keep it positive. Okay? So, enough of that. That leads to theorem 2. This is now the relationship between, all right, good to see you. I was tired of talking to myself. And I have my grade sheet here. 100. There's 227. All right. So Victor came in. This is the 30th. And so did Jasmine. Now, I got a phone call this morning from somebody who said he was in the class and working, and he ran I don't remember what he called it, split shift or something like that, and that he, so I was hoping it was Sylvester McCrew. Didn't catch his name when he first called, and he called right before my 8 o'clock class, and then he was staying on the phone. I said, look, are you coming to class today? He said, yes. He had the day off. So, well, good. We'll talk about it then, because I'm going to be late for class if I don't get up there. So, okay. Well, so far he's not here. So I don't know who it was that called, but hopefully it will be him. Okay. Now, let's get this flipped over. And since y'all are here now, let me just I think I made this announcement earlier, but I'll make it again since y'all are here to hear it. I don't have your Blackboard ready yet. I still have to check and make sure there's no new corrections to make to the syllabus. I thought I found something. I can't recall if I've corrected it or not. I've made the corrections to the research paper instruction. The locator card is ready to go. I've got to check on the websites and make sure that those are up to date. And I've got to make the link to Blackboard, to YouTube. And I've got to get the PowerPoint set. I have them, but I just don't have them imported into Blackboard yet. I've got one class completely done. Okay, I got that done basically, I guess it was over the weekend. I got most of that done. No, I got some of it done Wednesday evening, but didn't get to finish it. I thought I could work on it Friday, couldn't. And I worked on it a little bit more during the weekend, but couldn't get it finished because Blackboard wasn't up. And then I finally finished it on Monday afternoon. Now, that means this afternoon, I've got another 2 hours of office hours, finally. But I've got at least 2 requisitions I have to complete because they have to be finished by Friday. So I've got to get those done. I have the data on one, but I don't have the other. I've asked for it twice now, and I've got to see if they've sent it yet. So hopefully I will be able to make those requisitions this afternoon. And I have a stack of grading already from my physical science class, because that's a mini-term class. And that class has already done 1 lab and 1 test. And it's a fairly good-sized class, I think 20 students in it. So it's quite a bit of grading to do. So I've got to do that, and I've got to get my Blackboard set up for my other 6 classes. So I'm not going to get everything done this afternoon, but I hope to get a really good start on it. I'll take the stuff home again tonight and work on it. And I won't have any time to work on it tomorrow, but I'll take the stuff home so I can work on it Friday and over the weekend. So hopefully by next week I'll be back on it. We'll have Blackboard done and we'll be back on it. Okay. We had already introduced to you, and you'll have to listen to the first part of the YouTube to get this, but we're talking about the dot product. And I told you then, and I'm telling you now, there's at least two different definitions for dot product. Both of them are correct. Here's what the second one is. The first one we had already done, and the first one's pretty easy. Let's just say that vector V is a three-dimensional vector with components V1, V2, V3. Okay? Vector W is also a three-dimensional vector with components W1, W2, and W3. The dot product is then defined to be the sum of the products of the corresponding components. V1 times W1 plus V2 times W2 plus V3 times W3. Notice it's a scalar. Multiply two vectors together using a dot product, you get a scalar, a number, not a vector. Okay. Here's the other definition of a dot product. This includes the angle between the two vectors. And what we just talked about before y'all came in, I talked about it, was that when you have two vectors, they can be anywhere from 0 to pi. If you have two vectors like this that are greater than pi, you use the angle that's between 0 and pi. Because if you have two vectors like this, you don't go around like this, you just go between the two. So the angle between is the acute or obtuse angle between the two, nothing beyond pi, 180 degrees. With that in mind then, another definition of dot product is the magnitude of V, a scalar quantity, times the magnitude of W, another scalar quantity, times the cosine of the angle in between them. Okay? Now with that expression in mind, you can rearrange that and get that the cosine of the angle in between them is the dot product, which is easy to calculate, V1 W1 plus V2 W2 plus V3 W3, divided by the magnitude of V times the magnitude of W. That gives you the cosine vector. To get the angle itself, take the inverse cosine of both sides. Okay? And that will always give you an angle between 0 and pi. Because cosine, the inverse cosine is only defined between 0 and pi. Okay? That's the other reason we choose it. Okay? Because that's the only value it can be. Okay. Now, this they use a little bit in the proof, and since I'm not going to prove it, because this is just review material before we get to the real stuff. All right. Here's a triangle with the angle theta. The length of these sides are A, B, and C. Okay? Let's redo that as vectors. This is vector V, whose magnitude is A, vector W, whose magnitude is B, and if you don't realize already, this vector here is V minus W. Now, how do you get that? If you had done a V here and then put minus W here, this would have been the vector you got, which is exactly the same as that vector. So that is V minus W. Its magnitude happens to be C. Now, not that you really, I don't think you need that necessarily, but the dot product of these two vectors, okay, is going to be the magnitude of V, which is A, times the magnitude of W, which is B, times the cosine of the angle in between here. Now, I'm sure the proof used a bit more of that, but that's all we're going to do on it now. Okay? Now, here's another relationship. Okay? And this is part of that proof. The magnitude of that difference vector, that was the red vector there, that magnitude squared is, and this, by the way, is from your law of cosines. Remember that from trig? That it's called, from the upper part of that previous slide, c squared is equal to a squared plus b squared minus 2ab times the cosine of the angle in between. That's directly from the law of cosine. Okay? Like I said, they were going to use that for something else, and that's where this comes into play. All right. Okay. Now, from that last one, that first term on the right was that v plus w squared, which, by the way, is v plus w dotted with v plus w. Okay, that's one of those properties that we did before y'all came in. Okay, that any vector, let's call it u, the magnitude of u squared is the dot product of u with itself. Okay, so the magnitude of v minus w squared is the dot product of v minus u minus w with itself. Now, from the other property we talked about of what they called it, kind of like a distributive property, but it's kind of like foiling with dot products. Be v dot v, that's what this is, plus 2 times v times minus w. So it's a minus 2 v dot w, because you have one here, and one there. And they commute. So it's minus 2 times v dot w plus minus times minus plus w dotted with itself. Well, if you look at this, v dotted with itself is v magnitude of v squared. W dotted with itself is the magnitude of w squared. And then this is minus 2 times v dot w. Dot product there. Okay? And you might say, well, that's getting closer to what the definition is. That was in there, that was in there. What was here was something about 2 times, the cosine, okay? Cosine of theta. So, No, I'm sorry. Those were products, not sums. So anyway, leave that alone for now. And that yields, and I don't know. I've already told you this one. From the previous thing, cosine theta is equal to the dot product divided by the product of the magnitudes, and then take the inverse cosine on both sides and you get that. So that's old hat. We've already done that. So let's move on. And let's take a look at this. What does this picture show that is worthwhile? Maybe not much. Let's just see. All right, I guess it's just an example. Yeah, this is example 2. So we won't go into it in great detail, but let's just take a look at it. Here is vector V. 3, 4, 6. 3, 6, 2. All right, I can't read. Positive 3 on X, positive 6 on Y, up 2 on Z. Over here, vector W is plus 4 on X, plus 2 on Y, and up 4 on Z. Okay? Now, it's really hard to represent, to get a good grip on this when you're plotting a three-dimensional vector on a two-dimensional board. One of these is coming out of the board at a different angle as the other. But anyway, here is the, maybe not acute angle, but acute or obtuse angle between those two vectors. Not the angle over here, that's greater than pi. We want the one that's less than pi. That's equal to pi. Okay, so there's the angle. So if we were going to calculate the dot product, we know what, you tell me what the dot product of those two vectors would be. Have you calculated the dot product of two vectors? Sum of the products of their components. 12 plus 12, 24, plus 8, 32. That's the dot product. Pretty simple, and it's a scalar. Okay? Now, how do you get this angle theta? You take that dot product, what did we come up with, 32? Yeah. 32, and divide it by the magnitude of V, also divided by the magnitude of this. Well, what's the magnitude of this? V the square root of 9 plus 36, that would be 45 plus 4, that would be 49. That magnitude is 7, right? What's the magnitude of this one? $16, 4, that'd be 20 plus, which would be 36. Square root of 36 is 6. So this magnitude is 6, that magnitude is 7. Okay? So we have 32 divided by 6 times 7, that'd be 42. So 32 divided by 42, that gives you a number. Okay? Take the inverse cosine of that number, and you've got the angle theta. Okay? Were you doing it? See if I can remember what I said. 32 divided by 42 equal, take the inverse cosine of that. Be sure you're in radian mode, not degree mode. 32 divided by 42. Take the inverse cosine of that answer. In radians, not in degrees. Are you using a phone? not absolutely sure if phones will do it. They may. I don't remember if they have inverse trig functions on them or not. I think you can get them to the trig function. I don't know if they have inverse. You got an actual calculator? Okay, you can 32 divided by 42, and whatever that answer comes out to be, take the inverse cosine of that number. You're in degree mode. Yeah, be sure you're in radian mode. Just about everything you do in calculus, you should be in radian mode. 0.70, that sounds reasonable. That looks a little bit larger, but no, that looks like that could be 0.70. Okay, let's see what the book got. I wasn't going to do it, but they got 0.705, so good deal. They actually reduced there, as I said, 32 divided by 42, they reduced that to 16 divided by 21, and I get the same answer. Okay, so we got that. All right, here is another feature, property, useful thing to know about dot products. If you have two vectors that are exactly perpendicular to each other, they are perpendicular if and only if the dot product is 0. Meaning if you know the two vectors are perpendicular, you know automatically the dot product is 0. But more useful is if you find out the dot product is 0, then you know they've got to be perpendicular to each other. Another name for that is orthogonal. Okay? Perpendicular or orthogonal. Either one of those are perfectly good terms to use. When we did the dot product before, we found out it was 42. Nowhere close to 0. So those were not perpendicular. Even though, all right, here's Teddy. Good deal. Now, I was contacted by someone this morning when I was on my way to my first class, my 8 o'clock class. He caught me just before 8 o'clock, right before I was leaving the office to come here, and to come up to the classroom. And he started talking. I missed what his name was, and he said he was in the Cal 3 class, and blah, blah, blah. And ultimately, I said, well, are you going to, he wasn't going to be able to make all classes because he works. And he was wondering if he could, do some things. I said, I record every class, but I can explain all that. Are you coming to class today? He said, yes. I said, well, good, I'll explain it then. I'm late for class now. Oh, okay, yeah. And then he kept talking. So I was late for class. But I thought he was going to be here, and I was going to tell him what he needed to know. But he's not here yet, so he may still be coming in. We'll see. So we just have determined this. If any two vectors are perpendicular to each other, their dot product is 0. But even more probably useful, if you figure out the dot product of two vectors are 0, then you know they've got to be perpendicular to each other. Now, what I found a little alarming was in the last example. It looks like to me that angle is not too far from being right angle. It doesn't look like it's right. It looks like it's just a little beyond that. But frankly, that came off the dot product 42, which is considerably different from 0. Okay, so I was a little surprised it came out that big when it looked like it might be fairly close to perpendicular. Okay. Now, these three vectors, I think all of you should be familiar with them, are the standard basis vectors for space. Okay, this is for the Cartesian, you might say, space. Not spherical coordinates or cylindrical coordinates, but rectangular coordinates. These are your standard basis. They are mutually orthogonal. They are unit vectors, meaning they have a length of 1, and therefore their dot products had better be 0. I is the vector going in the direction of the x-axis, j in the direction of the y-axis, k in the direction of the z-axis, and they're unit vectors, so they go 1 unit in each of those 3 directions. So, if this was my origin here, I wish this corner thing wasn't here, but if this were, and we used 1 block, say, to be a unit, then 1 block on the x direction, 1 block on the y direction, 1 block on the z direction, that would represent those 3 unit vectors. Their dot products are 0 because they're orthogonal. Their magnitudes are 1 because they're unit vectors. So when the book doesn't make any special indicator that indicates something is a unit vector. I do. When I know something's a unit vector, I'm going to write like I with a caret over it. Most times vectors like vector, let me shrink this down. If I'm just doing any old vector v, I put an arrow over it because I can't write bold. The book writes in bold. That's how you know it's a vector. But if I have a unit vector, I don't put the arrow over it. I put a caret over it, a housetop, okay? So I, j, and k, okay? That's how I indicate something's a unit vector. And if we happen to have some other vector and we know it's a unit vector, like if we knew that u was a unit vector, I will put a caret over it rather than an arrow, just so you'll know not only is that a vector, it's a unit vector, okay? Now that's my little doing. The book doesn't necessarily do that. All right. Now, this I think goes with example 3. Just finished eating lunch. I tried to drink enough fluids, but I must not have because I'm beginning to clog up in my head again. I don't know. Or the room's cooled a lot. I don't know what it is. So here are 3 vectors used in example 3. And we're not going to do example 3, but just giving you an idea. U, V, or V, V, W, and U. Why would they name them that way? U, V, W would be alphabetical like that. This is vector U, which looks like it's plus 2 in X, minus 1 in Y, and plus 1 in Z. Okay? UV appears to be plus 2 in X, plus 1, 2, 3, 4, 5, 6. Looks like plus 6 in Y, and looks like 1 in K. Sorry. Yeah. In the Z direction. So, that is V. Vector W here appears to be a minus 1, 2, 3, 4 on X, plus 1 on Y, and it looks like to me to be about 1, 2, maybe 3, plus 3 in Z. Can't say that for sure. Yes, it could be plus 2. It's hard to say. But you can look at the example. All right? I think what they're having you do is check to see if any of these are orthogonal. How would you do that? Say again? Yes, doing the dot product of each pair. U dot V, V dot W, and U dot W, W dot U. And how would that tell you whether they're orthogonal or not? If it equals a 0, that means those two are orthogonal. Absolutely. I think that's what the problem was. I'll let you work it if you're interested. Okay. Now, the angle theta between V and U is obtuse if the dot product is negative. Okay? And here's the way to think on that. If 2 vectors are in the same direction, their dot product is magnitude of this one times magnitude of that one times the cosine of the angle in between. What's the cosine of 0? 1. So that's the magnitude squared. Yeah, we knew that, didn't we? Okay. The dot product of two vectors, or the same vector, is its magnitude squared. That's the maximum that'll ever be. As you start going up like this, the dot products now get smaller because cosine is going from 1 to 0 when you get perpendicular. So therefore the magnitudes are the same, but the cosine is reducing from 1 to 0. So anything in the first quadrant are acute angles, those are going to be positive. Perpendicular is going to be 0, right? And then when you get obtuse, the cosine of an obtuse angle is negative. It starts off being slightly negative and goes to -1, okay, when it's exactly in the opposite direction. So the angle in between those is obtuse if that dot product is negative. Something between 90 and 180 or pi. I've been saying 90, but should be doing pi halves. Okay. Without actually doing the exercise or examples, here's this one. Now this is another very common and frequent use of dot products. When we're talking about a projection of one vector along another vector, okay? Now, here's vector V, and here's vector U, okay? If you project U onto V, that would mean draw you a perpendicular from V or some projection of V up to the tip of U and then condense it. This is going to be the vector which is U projected onto V, okay? Now, they tell you here that projection of U onto V has a length of the magnitude of that projection, the magnitude of U itself times the cosine of this angle. Because if you think of this, here's the angle theta, this is the adjacent side, that's the hypotenuse, so the cosine of theta is U projection. Yeah, the projection of U divided by U, so the magnitude of U, okay. Let's see, what was I just saying? Yeah, cosine of the angle theta is projection of U, magnitude of this over magnitude of U. So magnitude U times the cosine of theta will give you the magnitude of that projection. Projection of U along V. Okay, so that's another pretty common application. Now you don't see a dot product in there, but we're getting there. We will relate that. So here is the theorem that relates that. All right. Assume that V is not the zero vector. If V is a zero vector, you can't project anything onto it because there's nothing there. Okay? So V can't be the zero vector. So the projection of U along the direction of V, that's the other reason. If V was a zero vector, it has no direction because it has no units. It has no, okay. So it's not the zero vector. So the projection of U along V is this vector. This is U projection. That's what that stands for. I like to think of it as the component of U parallel to V. That's why this symbol, to me, is a parallel symbol. Component of U parallel to V. Component of U perpendicular to V would be that. This is the component of U parallel to V. And that would be the dot product of U dot V. Now this is the unit vector along V, okay, multiplied by V, okay? The dot product of the projection, vector u dotted with the unit vector along v, that gives you a magnitude in the direction of v along the unit vector of v. Now, another way to express that is the magnitude of u is u dot v divided by v dot v. Okay? And that's multiplied by vector v, because see, this is a scalar quantity, because the dot product is a scalar, that dot product is a scalar. The quotient of two scalars is a scalar. Now, obviously, v can't be zero vector, because you can't divide by zero, so we're already taking care of that. And the dot product of a vector with itself is its magnitude. If it's not the zero vector, that's a positive value, so you're okay with that. So that scalar, u dot EV, which is the unit vector in the direction of v, is called the component of u in the direction of v. Okay. And that's what I was referring to as, and that's the same as projection. Yeah.
You said that dot product of v times v dot v is the magnitude?
Magnitude squared.
Magnitude squared. Oh, okay.
Magnitude squared. I may have just said magnitude squared. Okay? It's one of the properties of dot products. All right. This probably is with an example, so we're not going to linger on it too long, hopefully. What if it's an obtuse angle greater than 90? Then the projection of this vector v on u on v would be in this direction. There's projection this way. When theta is obtuse, the projection of u onto v and e to v point in opposite directions. So you think of this as sort of being a negative magnitude times that. Because if you go back to the former equation, this one, if that angle between those two is obtuse, then we know that is a negative number. So it points at the unit vector in the direction of v is pointing in that direction, but if that scalar quantity is negative, that flips it back in the opposite direction. Okay. All right, let's see what this one is showing. Just looking at it, I can't tell much. Let's see. Okay. This is what I was talking about before. This is why they're called U, the parallel lines there. The projection of U onto V, that's called U parallel, is what I like to call that. And U perpendicular would be the component of U that's perpendicular to V, and that would be U perpendicular. Okay? So anytime you have two vectors U and V, vector U projected on the V is the horizontal component of that, and U perpendicular is the vertical component of that. Okay. And that, of course, then yields, if you add the vertical component to the horizontal component, you get the vector itself. Because you're just adding this to that. You would say trapezoid rule, now it's rectangular rule. That is going to give you the vector u, the diagonal between that rectangle, of that rectangle. All right. I think this is an application illustration, and it certainly is. Have all three of you had physics, or are you just, some of you just starting it?
I already have it.
You have two, haven't you? Are you in physics? How you're in it now? Physics 1 or physics 2? 1. Okay. You probably haven't gotten there yet, but you'll be doing this kind of problem. The other two of you should have already done this kind of problem. Okay. I don't think, know if there's too much we need to do with that.
I think we'll leave it alone. I think you actually need to have the problem with it for it to make a lot of sense. So, but you use that a lot. I guess the thing you need to note, this is the thing that I always try to be very careful about when I'm working these problems. They're doing it slightly differently from what I would. That's your angle theta. Inclined plane, you're pulling that up, you're talking about the forces. Okay? Force of gravity's that way, you're pulling with the force that way. And that force must be what they're calling capital F. Here's L sub G, and there's your F that way. So what are those forces themselves? Okay? The parallel component, what you do then is set up your scale so you're measuring everything on the incline. So those forces are even. And what you do, if this is the angle theta, then, as they show you here, this is 90 minus theta, because if this is theta, and this is not, this is vertically downward, okay? So this is a right angle here, this is 90 minus theta here, and that's a similar angle to that. What I usually use is that is the angle theta there, because if this is 90 minus theta, that one must be theta, and then I use the relationships here. This component is the sine of that angle, over weight. Weight is the force due to gravity, and this here is related to the cosine of the angle theta, because that's adjacent to that theta. Well, this is the force perpendicular, which is your normal force that has to do with friction and that kind of stuff. This is your parallel force, which tells you what force he has to be pulling on the string. So this force, if that's in equilibrium, this force is equal to that. So it's just how you approach it. I don't usually measure on 90 minus theta. I just use that little angle in there as being theta. It works out the same. All right. I think this again is related more to a problem. Let's just see what they've got here. Here's a vector u, and its components, and this is, I hope it's intuitively obvious. In component form, that is vector AB. Okay, angle bracket meaning it's a vector, bold means it's a vector. Components are AB, XY plane, not three-dimensional, two-dimensional vector. Another way to express that, if this is the unit vector I, that's unit vector J. In two dimension, we don't have the K vector, so we don't worry about that. This is A times I, that's B times J. Because that's a magnitude, A, and that's how far it is out the x-axis. If your unit vector I is one unit out there, whatever A multiplied by the I is, that gives you the location and the magnitude and direction in BJ. So basically it's saying you can write your component form like this, or you can write it as AI with BJ, which hopefully you realized that before. I was trying to think, I'm not absolutely certain about this, but I think back when I took physics and calculus, I don't think we ever used the angle bracket notation. We used AI and BJ, and we called that the component form. This is a little neater and more concise. Okay? Now, if you're talking not about the coordinate axes, but you're talking about some other, say that vector V that you're comparing u to, that you're projecting u along or something, then you talk about its unit vector in this direction being E, and its unit vector perpendicular being F, and then this is u dot E in the E direction, and this is u dot F in the F direction. Okay, and that allows you either to rotate your coordinate plane, your axes, or to solve problems like you're doing with the inclined plane, or there's tons of applications of that.
We're not going to get into that now, but you may run into it in physics. Okay? Now here we're going to state again this property that I just stated or misstated before. The dot product of a vector with itself is its magnitude squared. Useful, very useful. We had it earlier. They're showing it to us again. I don't know why, but they're showing it to us again. Okay. Oh, this is from the summary. That's why they're showing it to me. They're summarizing the big important things. So here's the other one. This was what I called the second definition, because they did it second in the book, of a dot product. Magnitude of V times magnitude of W times the cosine of the angle in between. Scalar quantity. Magnitude scalar, cosine is scalar. Okay? Projection. I'm not going to go over all these again, but they're showing them again because they showed them in the summary as well. And that's the projection of U onto V, meaning the component of U parallel to V, is that. It shows several things about it. Okay? And then this was another way to express that. And I don't remember the second formula being there. It's in the text, but I'm not sure well, no, they didn't do it particularly. How they did it in the text was saying U is equal to U parallel plus U perpendicular. Here they just subtracted that. And what they're saying is, this is fairly easy to calculate. Then to get U perpendicular, just subtract it from U. Subtract the parallel from U, parallel component from U. Okay. Again, this is reiterating one we've already talked about. The component of U along V is U dot EV, which is magnitude of U times the cosine of theta. Aren't we missing something here? Is it usually magnitude of this one times magnitude of that one times the cosine of an angle? Guess what? Magnitude of unit vector is? That's why that. Just a little bit different way of doing it. Okay, that was 12.3. Blah, blah, blah. All right. Guess where we're going to go next? Just finished the dot product. Oh, I'm sorry. I hit the wrong thing. So guess what we're going to do now? The what? Cross product. You got it. If I can get it to pop up. Okay. Yeah, here it comes. All right. It's coming. All right. This happens to be the same picture in our text as it was in the last edition. So let's hit it. Don't know if any of you in either your study of physics or somewhere else have talked about or dealt with a bubble chamber. What a bubble chamber is you have highly charged particles fired into a chamber that has some fluid in it. That's a fairly stable fluid. And when the particles go through the fluid, they leave a track of bubbles behind them, sort of like the swimmer, leaving bubbles behind it. So does it, moving along there. And then if you do maybe time-lapse photography or something like that on it, you can trace it, especially if you have a way to color it like this and make it do. If that bubble chamber happens to be in a, say, a magnetic field, a charged particle moving through a magnetic field is going to feel some type of force on it. And that's why you get spirals and bends and things like that. Spiral paths of charged particles in a bubble chamber in the presence of a magnetic field are described using cross products. Okay? In fact, lots of things that way
fact, you get into magnetism much at all, electromagnetic theory, you're going to be in cross products. Okay? Sometimes this is also called the vector product. This is the same figure again in both texts, it looks like, because it was in the old one, since that's what I'm using on the slides, but it's exactly the same one in the text. The Van Allen radiation belts. Anyone heard of those? Those are belts that surround the Earth. They're located thousands of miles above the Earth's surface. They're made up of streams of protons and electrons that oscillate back and forth in helical paths between two magnetic mirrors set up by the Earth's magnetic field. That helical motion is explained by the cross-product nature of the magnetic forces. Okay. So lots of things use these representations. Sorry, I'm getting hard to breathe. So, I can't remember for sure, but I think you have several Van Allen belts, and these are some of them. You have to do it a little bit more. But notice they don't ever cross the pole, because the magnetic north and south pole, because it's places of where the protons and electrons oscillate back and forth, and they wouldn't do that directly over the poles. So they do it in these radiation belts. And I hate to say this, but I'm afraid I'll say it wrong. I believe that generally every time we used to send up space shuttles or any manned spacecraft way up there and coming back in, they were going to have to pass through these Van Allen belts. They were radiation belts. Now, there's also something called the ionosphere, and that's similar in results of it, but that's a different issue. But basically, when you were going through these things, because of all that radiation, and you think of a static noise, basically your the spacecraft and ground, you lose communications because the radiation just creates too much noise. Okay. I remember, I always get these crossed up. I think it was Columbia. Was that the shuttle that lost the heat shields and burned up on its way back in, or was that Challenger? We lost two, and it's one of them. I happened to be, my wife's niece was swimming and nephew were swimming in a young age swim meet up in Huntsville, which is a big space and rocket center, and we were up there at a swim meet, which was one of the most boring things ever created by man. Okay, and we were in there, and that was the time the shuttle disintegrated. And we were in there with a bunch of Huntsville folks, and you talk about the deathly silence that came over. Those meets are just nothing but a cacophony of noise because all the kids and stuff like this. Man, when that happened, everything got quiet. Everything was sort of stopped and suspended because that was a big deal in Huntsville. And I can't remember if they were passing through a Van Allen belt or passing through the ionosphere, but they were beginning to heat up then, and they were having some emergency sounding transmissions, trying to figure out what's wrong. Then they went into this place, and they lost communications, and they kept waiting for them to come out. They never came out. They disintegrated while they were in there. Not because they were in there, they had already melted and fallen apart, and everybody died, But it was really, really a scary time. But I remember that they weren't able to communicate, so they kept just hoping they were in the belt or the zone or whatever, and that they were going to come back on.
And they didn't. Okay, sorry. Now, one of the ways that we do cross products involves a matrix. Have y'all ever used that?
Yeah.
Okay. Basically the determinant of a matrix. Now, it's not usually a 2 by 2 like this, but we'll get to that. But here's what the determinant of a 2 by 2 matrix is. A matrix is an array of numbers. You can only take determinants of square arrays, and if you have a 2 by 2, A, B, C, D, the determinant of that is A, D, the product of A, D, minus the product of B, C. Okay? So, you're going to need to know that later for what we're going to be doing. All right. Now, if you had a 3 by 3 matrix, here's what you do. Pick one row, one column, it doesn't matter where. They happen to choose the top row. Okay? The determinant of this matrix is the first entry times the determinant of what's left over when you wipe out that row and column. B2, C2, B3, C2. So this is B2, C3 minus C2, B3. Say that. But when you go to the second one, you have to account for a sign. Okay? And let me just give you the sign convention in a real easy way. There's all sorts of complicated ways to say it, but if you have a matrix, 3 by 3, n by n, however big it is, start here and make it plus. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Plus, minus, plus, minus, plus, minus, plus, minus. However you go, as long as you go either horizontal or vertical, you're going to change sign every time you step down. So that makes this a negative one. So negative B1 times its cross product, A2, B2, okay? That's called minors and things like this. Plus C3, so A plus minus plus. So plus C at C1 times that determinant, A2.
Okay, I'm slightly confused.
What's that? You're what?
Slightly confused.
Okay.
So for A1, doing the cross product for
Okay. Yeah. This is just getting you there. Okay. To do the determinant of this, and we haven't said how this relates to cross products yet. We'll get there. But if you're doing the determinant of the 3 by 3 matrix, pick a row or a column. And when we do the cross products, it's always going to be the first row. So that's why they do it in the first row. So its determinant would be this value here, the value of that element here, times the cross product, the determinant of what is left over. That's called the minor. 1, 1, minor. Wipe out the first row, wipe out the first column, that's the minor that's left over. B2, B2, C3 minus C2, D3. Minus B1 times the determinant of it. What's left over there? It's minor. A2, C3 minus C2, A3. Plus C1 times its minor, wipe out the first row and column, A2, B3 together. The determinant of what's left over. That minor. Now, we'll get to why we're even bringing this up. This is in case you hadn't had linear algebra before or something like that to introduce determinants to you. Okay. So here's how you calculate a cross product. And I'm a little surprised this book chose this way to do it. But you see, this book is assuming we're going to be in 3 space. Okay? Space, rectangular coordinate 3 space. And if you are, and crossing 2 vectors, here's how you do it. The cross product of vector V, which is A1, B1, C1, and vector W, which is A2, B2, C2, is this vector. It's always a vector. Dot product of 2 vectors is a scalar. Cross product of 2 vectors is a vector. So what you do, you put your unit vectors, rectangular unit vectors on top, I, J, and K. I was writing with carets on top. Okay? And then you put the components of the first vector in the second row, the components of the second vector in the third row.
and then you do the determinants. Well, this is going to be times I, you know it is, so you do that minor, V1 C2 minus C1 V2. That's going to be the coefficient, that's going to be the coordinate of the I component of that cross product. Minus J, remember you've got to do the minus for that one, times this determinant, A1 C2 minus C1 A2. Plus K times the determinant of that one, A1 B2 minus B1 A2. However you want to do that. I got to sneeze. I think I'm right under the blower here, so I don't think it's anything to do with the mowing outside. But anyway, that's why they introduced, suddenly they just threw in determinants of a matrix. Why is that? Here's why. This is how you calculate the cross product of two three-dimensional vectors. This doesn't work for an m by m vector, 4 by 4 or 2 by 2. It doesn't work. It only works for 3 by 3. All right. So that's your definition of a cross product. Here's a, oops. All right. Okay. Before we get into that, it's a vector. Which way is that vector going? The vector, that's the cross product of two given vectors, V and W. Now, V and W don't have to be perpendicular. They don't have to be anything. But any two vectors are going to define a plane, right? Any two vectors are going to define some plane. Some plane. They could be close together. They could be way apart. But they're going to define a plane. So if it's V cross W, point your fingers with your right hand in the direction of V, cross them in the bend them in the direction of W. That's going to be the direction of your cross product. If V were where W is, and W were where V is, then it's going to point down. Okay, exactly the opposite of that. So V W U, where U is the cross product, forms a right-handed system, just like IJK would be right-handed. But remember, V and W don't have to be perpendicular. They more than likely are not. But U is perpendicular to V and U is perpendicular to W, because it's perpendicular to the plane, and those are in the plane, so it's perpendicular to both of them. But they are not necessarily perpendicular to each other. So that leads, or is included in Theorem 1. Basically, your geometric description of the cross product. The cross product, V cross W, of course they have to be the same dimension vectors, okay, is the unique vector with the following three properties. V cross W is orthogonal, the cross product is orthogonal both to V and to W. Because V and W have to be in a plane, and it's perpendicular to that plane. So it's perpendicular to both of them. Orthogonal. Number 2, V cross W has a length of, magnitude of V times magnitude of W. That's looking familiar, doesn't it? What's different? Sine of the angle theta, where that sine is the angle between 0 and pi between those two. So if V were here and W were here, you use this angle. If V were here and W were there, use that angle. You always use the angle that's less than pi. Positive angle is less than pi. Okay? Now, time out. What does that tell you about the cross product of two parallel vectors?
It's 0.
0, of course, because the sign of 0 is 0. Even if they're anti-parallel, they're still 0. Okay? All right. Anything else, we'll have a cross. And V, W, and the cross product of V and W form a right-handed system. Good deal. Now, seems like we've just seen this one, okay? This may be in an example. Yeah, it probably is. There are two vectors orthogonal to V and W with the same magnitude. One of them is on the plus side, one of them is on the minus side. That should have been self-evident, I think, okay? We use the right-handed one with your right thumb going up, okay? All right, the direction of U, which is V cross W, is determined by the right-hand rule. Boy, it's the third time they've said this. Thus, U has a positive Z component in this case. Okay. Oh, this is a particular problem. And they superimposed two slides on each other. They shouldn't have done that. Okay. The one in the background here is talking about two vectors. One is vector V, which is along the x-axis, 2, 0, 0. And the second one is vector W, which you can't see because we got this slide on top of it. It's 0, 1, 1. So it's somewhere right up there. And U is in the vector in that direction, not in that direction. Now, so it has a positive Z component. The other thing we were just saying is those two vectors that are anti-parallel with each other, W cross V has to be the other one in the opposite direction. Same magnitude, same everything, but in the opposite direction. That's equal to minus V cross W. So guess what? Cross products are not commutative. Dot products are. Cross products are not. They're always negative with each other. So they're not equal to each other. So those two things were thrown into the same slide. They shouldn't have been. Here is that one separate. Whoever put this together, had a little error there. Okay, this says it all. D, this is V, that's W, V cross W is there. If you do W first cross with V, it's anti-parallel to the first one. So it's exactly opposite. So that means cross products are not commutative, ever. Okay. And that's what I was just doing with my hand. They're doing here. Let me blow this up a little bit. V cross W would be up here, whereas W cross V would be down that way. Always opposite, exactly opposite of the other. All right, that leads to the basic properties of cross product. All right. Top of page 656. Cross products are not commutative, they're anti-commutative. They're exactly opposite each other. U cross V, V cross W is exactly the negative of W cross V and vice versa. And, as we just said, V cross itself, or anything parallel to itself, is 0. Okay? Now, what if you had two vectors, V cross W, do you know they're 0? Can you say then they're definitely parallel? They could be, but it could be that V is a 0 vector, or that W is a 0 vector, or that W is some scalar quantity that is a multiple of V. Okay? So they don't have to be the same vectors. They could be just a multiple of the vector. So if this was V, this could be W, that could be W, or this could be W. Anytime, if that cross product is 0, or V itself could be 0. Okay? So, or W itself could be 0. So it has a few more possibilities there. Number 4, a scalar times a vector V crossed with a vector W is the same as the vector V crossed a scalar times W, and that's the same as a scalar cross times Yeah, that looks just like the corresponding rule for dot products. These not necessarily, but these, that one is the same. Now here's the sort of weird one. Now this one you have to be very careful of your order, okay? If you have the sum of two vectors, u plus v, that's going to be a vector. Cross that with vector w, that's going to give you u cross w plus v cross w. You can't just arbitrarily change the order. That would change the direction. Or if you had u cross with the sum of two vectors, this is just the backwards of this, that's u cross v plus u cross w. Okay? You can't interchange those. You have to keep them in the right order. Cross products are that way. All right. Now, these are some hopefully fairly obvious relationship. I cross j, x cross y is positive z, j cross k is positive I, k cross I is positive j. Okay? As long as you keep them in the order ijk, 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 as they're in that order, then they're positive. If you get them out of that order, j cross I, those would be negative k cross j, negative I cross k, negative j. And I cross itself is the same as j cross itself, it's the same as k cross itself. There's a parallel, the same vectors there, not cross product. Notice that's not the number 0, the scalar 0, that's the vector 0. Strange. 0 components for everything, 0, no direction, no magnitude, but it's a vector, okay? Because the cross product is a vector. Okay. Here's another way to express what I was just saying about the ijk. As long as you go in that order, ijk, as long as you go clockwise here, you're going to have I cross j is positive k, j cross k is positive I, k cross I is positive j. If you go the other way, I cross j, k, negative j, k cross j, negative I, j cross I, negative k. So if you go clockwise, you'll get positive. If you set them up this way, ijk, go clockwise, you get positives, counterclockwise, negative. If you find that useful, use it. Okay, I believe this is probably associated with a problem. But as we said before, if you have a charge, a moving charge in a magnetic field, it's going to experience a force. And that force is a cross product force. So this goes to which law of physics it was called. V cross B, the force is always V cross B. So V cross B is the forces in that direction. A proton, positive charge in a uniform magnetic field which is up is going to, so if the velocity is in a j direction here, it has to be a negative j here, cross with a magnetic field in the k direction, because it's a negative j, that's going to give you a force in the negative I direction. Okay? That's what that's illustrating. Now, if that were an electron, now you have a negative charge, so that will flip it around and the force will be in this direction, because that's like having a negative alpha, a negative lambda in front, negative 1 in front, it changes the direction. But you get this helical path, okay? And then looking down on the bubble chamber, that's how you got those spirals in it. Okay. I'm not sure that these make any sense outside the problem they're talking about. These are just a couple of
applications, you might say, of cross products, areas and volumes. The area of a parallelogram, P, that's the little N region there, is V cross W. V is the downward leg, W is the upward leg, and V cross W, which is magnitude of V as the magnitude of W times the sine of the thing, magnitude of W times sine of V. Yeah, that's going to give you exactly the area of the parallelogram defined by those two vectors. Interesting. Now, how about the volume of a parallelepiped? Okay, that is going to be something a bit weirder. Okay, and that's going to be U dotted with the cross of V and W. Okay. All right. Here is U, here's V, and here's W. The volume of the parallelepiped formed by that is cross the V, cross W, dot that with the U, and that should give you the volume of that parallelepiped. So we're not going into great detail on that. If you ever need it, there it is. You've seen it. Look it up. All right. This is doing some of the calculations from that, which is the, again, using matrices and determinants of matrices. They've left out a lot of steps here. Okay, obviously the vector U is A1, B1, C1. The vector V must be A2, B2, C2. The vector W is A3, B3, C3. That sort of irritates me they do it this way. So much easier to keep track on if you name those components U1, U2, U3, V1, V2, V3, and W1, W2, W3. You don't have to keep up now which one is U, which one is, they're obvious then. But this is correct the way they did it. Now, this cross product, skipping the steps where you did that, that gave you that determinant times I, this determinant times A, minus that determinant times A, plus that determinant times K. Then when you dotted this, you merely are multiplying this first component by the first component here, minus the second component by the second component here, minus the third component of this, plus the third component of this, minus the third component of that one. And, what does that give you? If you work that out, that's just the determinant of U, V, W. Interesting. Okay? So you can actually skip some of those intermediate steps and go straight to this. Now, if you know the rules for taking determinants, if you've had linear algebra, you will find that's sometimes easier or harder to do than others, but there are some shortcuts you can take because you don't have to go the first row or anything else. Basically, you choose the row or column with the most zeros in it and use that one. And it makes life so much easier.
And something that is a scholar, right?
What's that?
Like, if you do this process, it will become a scholar answer, right?
Yeah, scalar answer.
Yeah, scalar.
Yeah, right, yeah. The dot product of a vector with a vector is a scalar, and the volume of a parallelepiped is a number, is not a vector. Yeah. Whereas the other one, where was it? Did I skip it? Yeah. This one, area is a number, but you take the magnitude of the area, which makes it a scalar too. The cross product is a vector, but the magnitude of the cross product is a scalar. Okay. Whoops. All right, this is the next one. I'm supposed to be doing these fast, but there's so much in them that it's hard to do them very fast. Okay, area and volume via cross products and determinants. Basically, it's summarizing what we just did. Let U, V, and W be non-zero vectors in R3. The parallelogram P spanned by U and V and W.
U's not involved with this at all. V and W has the area of the magnitude of the cross product of those two vectors. Okay, done. The parallelepiped, which is a volume, it's a space figure, not a planar figure. P, yeah, make it a bold P, spanned by U, V, and W, has the volume that is the determinant. Now, be careful here. It's the determinant of these three, okay? Where you put U in the top row, V in the second row, and W in the third row, and take the determinant of that. Now, it's not just the determinant. This is the absolute value of that thing. This gives you a scalar product, but that scalar may be negative. If it is, take the absolute value off. So usually if you use double bars to represent the determinant, but now they're using these double bars as absolute value of the determinant of those three, which you could have used another set of double bars. And that gives you the volume of the parallelepiped. And you don't have to worry about any angles at all. This gives it to you, which is nice. All right, I think this is a problem. You know, there's one more done in our text that's not being done on the slide set here, and that's the area of a triangle spanned by U and V, not the parallelogram spanned by that. Basically, take half of it. Okay? Go back to this picture. If you do the triangle here, this area is exactly half of the area of that parallelogram. So that's what we mean by that. It doesn't show up on these slides. It is in your book. Okay? Now, that's figure 10. I think that's an example. Okay? And you can play with it if you'd like. It's perfectly fine. Okay? Here's another example, I think. All right. And then I think this is also part of an example, but it's phrased a little differently. Okay? If A is an area of a parallelogram, okay, that's the absolute value of the determinant of V and W. But that is indicating a two-dimensional vector. It's not necessarily a two-dimensional vector. Oh yes, it is a two-dimensional vector. This is figure 13. So if you have two two-dimensional vectors, parallelogram is even easier to do. Okay? Of course it would be. That's the figure for what we're just doing. That's the two-dimensional vector. Two-dimensional vectors, U and V, V and W. All right. Two dimension. If those are, then the area of this parallelogram is exactly what that last formula was. Just do the determinant of those two. Okay. And then the triangle formed by those would be. Say that, but it's still true. All right. This, I think, is just reiterating. Oh, yeah, this is part of the proofs for the thing, so they just restated them. It's exactly what we saw earlier, so nothing new there. This is something new. Okay. Well, no, not really. This was part of the proofs we did before. Maybe we didn't quite get this far, but that's... that is part of this. The magnitude of the cross product of this squared is the magnitude of the first squared times the magnitude of the second squared minus the dot product of those two squared. No, we didn't do that, but that is indeed another property that sort of crosses cross products with dot products, ties them together. Okay? This is going to proceed to show that this is the left-hand side of that last one, V cross W, magnitude of that squared, and that's its representation. This is the right-hand side of that, whoops, the right-hand side of that former equation. That's magnitude of V squared, magnitude of W squared, minus the dot product squared. And this does all that for you there. Remember, magnitude squared is the, this is A1, B1, C1. And that the magnitude of that would be the square root of A1 squared plus B1 squared plus C1 squared. But then if you square it, you lose the square root. So that's what that comes out. This is that, that's that. And then there is the minus the dot product of these two, which is A1, A2, B1 plus B1, B2 plus C1, C2. And then you square that. Some nasty thing to square. Of course, that's also a nasty product of two trinomials. So you got at least 6 terms out of that. So if you do all that and subtract things that you can subtract or whatever, then you turn out getting the right hand side. Okay, this is almost a rehash of what we've had several times. Let's see what that says. Both V cross W, V and W, and V, W, and V cross W are right-handed. Of course they are. If you look at this, if you start with this as your first one, 1, 2, 3, and then do the same order, either 2, 3, 1, or 3, 1, 2, this is your 3, 1, 2. So as long as you keep them in that same order with crosses, you got a right-handed system. So yeah, that works there. All right, here's a summary. There's that IJK thing again, just like we showed it before. They're showing it again for the summary, and I think that's it. Whew! And are we out of time? Is it? Yuck! I didn't know it was going that fast. All right, we'll begin next time with planes in 3-space. This is 12.5. It's fairly short. Hopefully we'll get through it very quickly. Then we'll finally be in quadric surfaces, which is where this Cal 3 technically begins. But we really needed to catch all that up so that everybody was on the same page, kind of to start with. Okay? So we will start with planes in 3-space. It shouldn't take us but a short while to do that, and then we'll move from there. Okay. Good deal. Now, someone remind me, is Monday Labor Day, or is it the following Monday? Monday is. So I've been telling the classes so far, have a good weekend, see you Monday. I won't, okay? No class on Monday, Labor Day, which really is a pain because we're already a little behind. That puts us even further behind. We'll try to pick things up. Like we covered 2 sections today fairly well. So. Okay? But we're going to start doing exercises, so that will slow us down a little bit. So, see you next week. And by the way, you can work any of the homework exercises into these sections. The odd numbers are in the back. If you want to refresh yourself on dot products, cross products, or anything else we've done so far.
Okay.